Isn't he just adorable? I just had to start with that today. Okay, so we're going to talk about carboxylic acids today. And these guys are pretty easy to name. See how this would be a chain of 3 carbons? That would be propane. We remove the E and add oic acid. So that's propanoic acid. This still takes number 1 because that's the carbon that has the carbonyl. It also has the carboxylic acid there. So this is now 3-bromobutanoic acid. If you have something where you've got a carbon that's sticking out from a cyclo ring, then that becomes just carboxylic acid. So this is, I'm sorry, that should say cyclopentane, shouldn't it? So cyclopentane carboxylic acid. Pentane. Okay, good. This would be a carboxylic acid. So we call that propane dioic acid. And if you take off the hydrogen, because remember, these are named acid for a reason, if we take off this hydrogen by having a base present, these become carboxylates. So that's what we call these guys down here. And what we do is we start by naming whatever the salt is or the counterion is here. And that becomes potassium propanoate. This is how I remember it, okay? Because the O ate the hydrogen. Get it? Okay, no bad, but it's true. That's how we name them. Remember, this is still an sp2 carbon, so these guys are flat. But the reason why carboxylates are so stable, so the reason why carboxylic acids are so acidic, is because their conjugate base is stabilized through resonance. Remember, resonance is going to trump any type of inductive effect. But what that means is that there's a strategy for looking at how acidic each of these hydrogen are on different types of carboxylates, or I'm sorry, on different types of carboxylic acids. Apparently I said this wrong before, but these are not in resonance. They are actual resonance structures of one another, okay? What actually exists is a hybrid form between the two of them. So the strongest acid has got the most stable conjugate base. That is so very important. That's something that I see issues with quite frequently, really from many standpoints in chemistry. So when we're looking at comparing acidity, what you really want to look at is how stable is a conjugate. It's kind of like thinking about if a family has, this is the analogy I use in class, sorry, this is kind of silly, but if a family is going to let somebody from a college perspective go to college and leave the family versus if they're going to kick out the baby. The person that's going to college hopefully has a little bit more skill and stability of being on their own than would be a baby. So you have to think about that. The one that's more likely to be in that position where they will leave would actually be the one to leave, okay? And so that's why it would be a stronger acid. So the more resonance structures you have, the better off it is. The more acidic something the parent carboxylic acid would be. And resonance structures are going to beat inductive effects in that process. So here's what I mean by that. Okay. This would be the least acidic, but as we start adding electronegative atoms, this would be a little bit more acidic. But when we put the fluorine closer to where this guy is, that actually makes a big difference. So the first carbon next door, having that fluorine there, is where the inductive effect is seen the most, okay? As you get further away, that inductive effect is not really that strong after a certain point. Having 2 is always better than having 1, which is better than having none. So that's why this one would be the most acidic of this group. And so when you're looking at acidity, oftentimes you are comparing the acidity of one versus the other. It's hard to say without just looking at the pKa what you're really comparing otherwise. Okay, so down here, something to note. This would be the least acidic, and this would be the most acidic. So again, let's think about the conjugate base. Let's think about what these things do. If you were to have a conjugate base, that means you have a negative charge up here with a COO minus. We need to stabilize that. Well, remember, this guy is activating because he's pushing electrons into the ring. So does that help a negative charge get stable? No, it really doesn't. Meanwhile, over here, these electrons are pulling out of the ring. Does that help stabilize a negative charge that might come up here? If you look at the resonance structures, you will see that that indeed does happen. So that is going to be the most acidic of these three, and this would be the least acidic of those three. Just having nothing there is actually in the middle. Okay, so just as a review, these are all things that you've seen before, I think. We can make carboxylic acids. We can make specifically benzoic acid from any R group hanging off of a benzene, as long as you have a hydrogen. So all you need is one hydrogen, right? You can also make it from an alcohol with Na2Cr2O7, acid and heat. Okay. There's ozonolysis. Remember how that cuts that bond right there and leaves behind fancy oxygens all over the place? And that's where these guys come from. We can use a Grignard with CO2 followed by water, because this guy is going to come in here and attack that carbon, and that's what you've got here, right? COO, and the H comes with the water there. And as we saw last time, we can take a cyano group and knock that down with acid and heat and turn that into a carboxylic acid. Okay. We can also reduce carboxylic acids with lithium aluminum hydride. This is a little bit different from what we saw before when we were looking at hydrides. But the same thing really is happening, is that we end up with, 3 carbons there and an alcohol. But here's what's different. With a carboxylic acid, remember, you've got a proton here that's ready to leave. And basically this guy's H-. So what happens is this H- comes and attacks this H+, and together they make H2 gas. And you can watch it bubble straight out of the reaction. And that makes electrons fly up. And this kind of clinging happens. Aluminum loves oxygen. So it kind of clings to that oxygen. It's kind of a bond, it's kind of not, but it's semantics as to which one's really happening in some ways. And what can happen here is that this hydrogen from an AlH3 is coming back, and he's coming back and touching right there, and electrons come up. Okay, now what you've made, like we've seen with SOCl2 and things like that, is you made a really good leaving group. So these electrons come back in, and this entire thing leaves. And what you're left with is a C-double-O bond that we know reacts with lithium aluminum hydride, or any hydride for that matter. So what you can do is just this guy comes back in here, he goes back up. Once you have those electrons around that oxygen, that's going to be acidified, and there you go. And that's it. Thank you very much.